Hi and welcome to 1.4 Graphically Adding Vectors. So if you have a ruler and protractor at home, now is the time to break them out. The first thing we'll do is some parallelogram rule. We'll set up the vectors, and then we'll set up the vectors using head to tail. And then we even have this. Now, typically you would measure this with a ruler, but if you're working at home and you don't have a ruler or you don't have this worksheet printed out, that's why I gave you the measurements right there. So you don't actually have to measure it because it's written there for you, but you could, like I didn't have to tell you what this was. And then you'd have to measure it with a ruler and see what the scale was. Okay, so you need to know how to use a ruler in this class. Eventually, but for this one, we'll work around it. When I redraw the vectors for this, I'll make them blue. So it'll look like this. You make that, and then I'll make the resultants. As always, the resultants are going to be red. So let's get started. Number one, we're going to use the parallelogram rule to carefully construct the resultants for the vectors below. If we had this sheet in front of us, we could use a ruler to redraw them. I'm going to have to eyeball it. I'm going to redraw that vector pointing up. It was originally pointing up, so you want to make sure it's pointing up. And then the one below is pointing to the right, so you make sure it's pointing to the right. Now we have a rectangle, aka a parallelogram, and we draw from the tails to the heads, and that is the resultant, a red vector pointing up and to the right. For number two, we have a vector that's pointing to the right, so I'll draw it right here to make it like kind of to scale, and then I'll move it so that it's head to tail. Try my best here to move it in place, kind of like that. Okay, not the best situation. And we should be able to do the same process over here, and I'll move that over. And for situations like this is where the parallelogram rule really shines. But you do need to have a protractor handy to make sure you're making the angle correct. Okay, if you were really doing this graphically, you have to make sure the angle is absolutely the same, or just, if you make this one the same length as this one and you make it exactly to the right, very precisely, then your scaled vector diagram will work out. The whole point is you can use this ruler to measure the length of that vector, and that'll tell you the magnitude of the resultant, and you could use a protractor to measure that angle, and it'll tell you the direction of the resultant. So that instead of doing trig, you could use a ruler and protractor to find the magnitude and direction of these resultants if you set them up correctly. So again, I'm going to do to scale this arrow going up, and I'll move it over so it's head to tail. If you were doing this at home, you would just measure that with a ruler and then redraw it in the position I showed there so that it's head to tail, and then you finish your parallelogram. I'm just kind of freestyling that one a little bit, but it could be better if I had a ruler and protractor. And then from the tails to the heads, and you get an arrow pointing up and to the right. That's your resultant vector. Okay, we'll do the same thing. We'll just redraw both of these. So this vector goes head to tail. You measure this vector, and you make that go head to tail. You redraw it. And now you have a parallelogram, and then you could draw from where they start to where they finish. And that's a cool way to do adding vectors, the parallelogram method, if you like doing it that way. To me, I like to be efficient. Really, I like to be lazy. You see how we're redrawing both vectors? If you just do the head to tail method, you only technically have to redraw one vector so that they're head to tail. And then you could stop there and draw the resultant. So that's technically less work because you're only redrawing one of the vectors. So let's try it that way. We're going to use the head to tail method to find the resultants below. You could still do the parallelogram method for these. We're just practicing a different venue. So you could redraw either one. I'm going to redraw this one and move that so that it's head to tail. I have a fancy situation here, but you would just use a ruler to measure the length of that vector and then redraw it going down because it's going down initially, and you redraw it at the head of the next one. So now they're head to tail, And just like we did in 1.3, adding vectors, we're going to draw from start to finish. So the first step when you're adding the vectors, draw them all head to tail, and then you draw the resultant from start to finish. We'll do the same thing over here. And here's a tip, since this one is at a weird angle, I don't feel like, breaking out my protractor and trying to match that angle. Luckily, there is one that's just pointing straight to the left. So I would redraw this one on the other one. And you just connect them head to tail, kind of like this, okay? You could, for all of these, you could also draw like that. Is that head to tail? Yes, and you would still get a vector that points down and to the right, like this. And I could copy this one just to show you. Duplicate, boom. Look at me with this fancy, this is called Drawboard PDF if you ever want to draw on PDFs, just so you know. I'm doing it twice, I'm doing double work just to show you that the vectors, now we're doing start to finish. Again, you don't have to do this. Again, I'm just showing that either way you do it, you get the same resultant, okay? As long as you're very precise about it, okay? So that's not what the answer would look like. I would only do it once, and I would probably do something that looks like that, okay? So the resultant is in red. All right, so number 7, like I said, if you had a ruler at home and you printed this out, it should be to scale even when you print it. You could measure these lines, and this line should be 5 centimeters long and this should be 3 centimeters long. But to work around the fact that we don't want to really print out everything, I'll tell you what the sizes of them are. So it says determine the scale used in the vector diagram. You could choose either one of these numbers to work with and you should get the same answer. So it doesn't really matter, but we'll start with maybe the 15 unit vector. So 15, well, it doesn't matter, 15 units, we'll make the units on top, is to 3 centimeters. We want to know how many units does 1 centimeter equal. That's what they're asking. So you set up the proportion to find the scale. The proportion for the scale will always work if you do this method correctly. And you set up units on top, centimeters on the bottom. So you cross multiply and you get 3x is equal to 15. And then you divide and you get x is equal to 5 units. You might have been able to do that in your head just by looking at the numbers, but the process is super important to know, okay? I'm going to make that a little smaller so it's out of our way. Now we are ready to draw the resultant force vector. Oh, so I copied this from Unit 4 when we talk about forces. So you might be like, what the heck is a resultant force vector? I said it before, a vector is just anything that has a magnitude and a direction. And a force is an example of a vector. But you could also have displacement vectors and acceleration vectors and velocity vectors. All right, so this one happened to be, I copied and pasted, it's a force vector. But we'll just call it a vector to be simple, okay? And then instead of a force being measured with newtons, which it should, the units should be newtons, because I'm just noticing now that this says force, all right? But we'll keep it in units because that's what's shown over here. There's no unit on there, so we'll just say units. Anyway, so let's draw the resultant. And everybody's super excited to make a right triangle. So let's draw the right triangle. Okay, and for some reason, when we have an arrow pointing up and an arrow pointing to the left, we drew a resultant that's pointing down and to the left. Wait a second, that doesn't make much sense. I must have done something wrong. Okay, so let me draw the arrow going this way. So now we have an arrow pointing up and an arrow pointing to the left, and we get something that's pointing up and to the right. What the heck am I doing wrong here? There's no way a resultant of left and up should go in those directions. What did I do wrong? How are these vectors connected? Tail to tail. How should they be connected? Head to tail. So you could either do the parallelogram or the head to tail method to redraw the vectors. I'll do the head to tail method. I like that one better. So you measure, if you were doing this with a ruler, You'd have to measure exactly how far is that, get as precise as possible, and then redraw it. I'm doing it differently, like obviously because I'm on this Drawboard PDF app, okay? But you would redraw it with your ruler and a pencil, and try to get right as close to the head. Oh, that's looking pretty good like that. Okay. Now you can draw your resultant vector from start to finish, and you could label it R. Okay. Letter C says determine the magnitude of the resultant vector. At this point, if you were doing this with a ruler on a piece of paper, you could just measure this length and use the scale. You'd have a number in centimeters. You could use the scale to find how many units long that vector is, which is pretty cool. You don't have to do any trig at all. You're just using a ruler and a scale. It's a scaled vector diagram. I think it's cool. If you're into like drawing, this might appeal to you. Any kind of like art where you're a little bit creative, you get to construct something on a piece of paper. Maybe this appeals to you, right? So, but if you're more into the math, maybe you like doing it algebraically. Since I can't measure this with a ruler right now, I'm going to have to do it algebraically. So I'll show the work so you can kind of see what the answer should be. You should get an answer of about 29.2 units, okay? If you were doing this graphically, you would measure the hypotenuse and you would get about 5.8 centimeters when you measure it with a ruler. And then the real point of this is we've done the trig stuff so much. The real point of this is to use the scale. So I'll show you how to scale it up, just in case you're doing this on a piece of paper with a ruler. So we know our scale is 1 centimeter is to 5 units. And we know how many centimeters long this vector is. We want to know how many units that's equal to. So again, you can cross multiply and you get x is equal to 29 units, which is totally acceptable. You know, the trig will give you a more precise answer every time because we're just using a centimeter ruler, and the best we could do is like maybe measure the millimeters. That's how we get the 0.8. But the decimal goes further than that. Which is why this is a little bit different, but they're both totally correct answers. They're both acceptable ways to find the magnitude of the resultant. I think the coolest thing, I love using protractors. I don't know about you, but once you really know how to use them, instead of doing, who wants to do inverse tangent every time? Wouldn't you rather just throw a protractor on the paper and be like, okay, it's that many degrees, done. Like, why do I have to do the inverse tangent every time? It's such a pain. Go in my calculator, just throw the protractor on the paper, then you're done. So I think it's kind of cool, right? But I'll show the trig work, and that's the angle that you should get. You know, there's no scale that needs to happen with that, which is another cool thing, is you're directly measuring the angle, which is pretty cool. So I'll show the inverse tangent work. And your calculator spits out 30.96375653. All right, so but if you were directly measuring this with a protractor, it would be cool if you got, instead of 30.96, it would probably look like 31 degrees, and that's totally acceptable for our purposes here. Now, I did want to mention, so this is, again, super important right at the end of the video. Look at the wording of the question. It says, determine the measure of the angle in degrees between north. They're calling out a specific angle between north and the resultant vector. So north is here, the resultant vector is here. Luckily, we found this angle, okay? If you drew your vector, maybe you did the parallelogram method, or maybe you just redrew this one and it looked more like that, maybe you wouldn't have been inclined to find this angle. Maybe you had a triangle there that looked like that, and your instinct would have been to find this angle. But if you said that angle, you would have been wrong unless you specified, if you write north of west, that many degrees north of west, then I could say, what is it, 59 degrees north of west. And you specified that I'm telling you that particular angle, maybe you'll get points, right? But they're specifically asking for the angle between north and the resultant, and the correct answer is 31 degrees, not 59. All right, this is not a 59-degree angle, so if you just wrote 59 over here, you get that wrong, unless you say 59 degrees north of west. Then you're calling out this different angle. Yeah, it's different, but at least you're showing that you know what you're talking about. And this one, you don't have to, but just so you know, this is west of north. This many degrees west from the northern direction. Okay, that got a little bit more complicated than it had to, but I'm warning you. That's going to be on like tests and quizzes, and it might be on the Regents and the final exam. So fair warning here. Fair warning. You have to answer the question that they're asking between north and the resultant. And that's about it. Have a great day.